Welcome to Simple Physics. In this session, we are going to see about the three kind of particles under statistical thermodynamics. The first type, the particles are identical but distinguishable particles without any spin. So the particles of this type are molecule of a gas. Example, we can take oxygen molecule. Any type of gas we can take. So one of the example is oxygen molecule. And Maxwell-Boltzmann distribution function holds for such a particle. And the second category of particles are identical, indistinguishable particles of zero or integral spin. These particles are called as bosons, and these particles do not obey Pauli exclusion principle, and Bose-Einstein distribution function holds for them. Example of these particles are helium atoms at low temperature, phonon, meson, alpha particles, and photons. The third category we will see now. The third type of particles are identical and indistinguishable particles with odd half integral spin, half, 3 by 2, 5 by 2, etc. The spin may be. Their wave functions overlap on each other, and these particles are called as fermions, and these particles obey Pauli's exclusion principle. Electrons, protons and neutrons comes under the category. These particles comes under the category of Fermi-Dirac statistics. These particles are also called as fermions. Fermi-Dirac statistics is used to study the behavior of free electrons in a metal, whereas Bose-Einstein statistics is used to study about the black body energy spectrum. The radiation that was emitted from the black body can be studied using Bose-Einstein statistics. In this session, we see about the classical and quantum statistics under statistical thermodynamics. There are two types of statistics, classical as well as quantum statistics. Maxwell-Boltzmann statistics comes under the category of classical statistics. Bose-Einstein statistics and Fermi-Dirac statistics comes under the category of quantum statistics. In classical statistics, Maxwell-Boltzmann explained about the velocity and energy distribution of particles in an ideal gas. So, gas molecules are the particles under classical statistics. But in quantum statistics, you can see there are two subclasses. We can categorize this quantum statistics as Bose-Einstein statistics and Fermi-Dirac statistics. So, the particles that comes under the Bose-Einstein statistics are called as bosons, and we can categorize these into two depending upon whether the wave function is symmetric or antisymmetric wave function. So if the particle possesses symmetric wave function, it comes under the category of Bose-Einstein statistics, and if the particle possesses antisymmetric wave function, it comes under the category of Fermi-Dirac statistics. Now we will see about what is this symmetric wave function and antisymmetric wave function. Symmetric wave function, so the wave function, so R1, R2, R3, these are all the position vector of the particles. So assume a system consisting of number of particles. So if you interchange the particles, any two particles, if the wave function remains the same, there is no change in sign, then such a wave function are called a symmetric wave function. But if on interchanging the particles, that is here you see R2, R1 instead of R2, R1, if you interchange that as R1 and R2, a negative sign arises. So in this way, if the sign changes, if you interchange the particles, then such a wave function, it is called as antisymmetric wave function. So the particles having symmetric wave function comes under the category of Bose-Einstein statistics, and the particle which possesses antisymmetric wave function comes under the category of Fermi-Dirac statistics. Bose-Einstein statistics. Under this, we will see about some of the significant points of these statistics. This statistics was developed by S.N. Bose, the scientist S.N. Bose, while he did research about light quanta, which is called as photons, and this statistics was generalized by A. Einstein, and this scientist A. Einstein, he alone gives the energy distribution of these particles, how the energy can be distributed in bosons. He described about the energy distribution under the statistics. For these particles, the spin angular momenta is found to be NH cross. N is equal to 0, 1, 2, 3, etc. And these particles are called as bosons. The wave functions of these particles are symmetric wave functions. I already told symmetric wave functions are nothing but if you interchange any two bosons, the wave function remains the same. Then such a function, we are calling that as symmetric wave function. And these particles do not obey Pauli's exclusion principle. The spin of these particles are zero or integral spin. It takes only zero or integral spin. So example for these particles are alpha particles with S is equal to 0. S represents the spin quantum number. So these particles have 0 or integral spin only. Photons with spin is equal to 1. Neutron with the neutron particle with spin S is equal to 1. Pi meson with spin quantum number S is equal to 0. So these are the example for these particles, that is bosons. All these particles comes under the category of bosons which do not obey Pauli's exclusion principle. The energy distribution of these particles are explained by the scientist, and it was developed by S.N. Bose. Under Fermi Dirac statistics, we are going to see about some of the significant points. This statistics was developed by E. Fermi for electrons, and its relation to quantum mechanics was done by the scientist P.A.M. Dirac. That's why this statistics is called as Fermi Dirac statistics. The particles that comes under the statistics are called as fermions. These particles have the spin quantum number S is equal to n plus half h cross, where n takes the value from 0, 1, 2, 3, etc. If you substitute 0, the spin quantum number becomes half h cross. So these particles have odd half integral values. The spin of these particles are odd half integral values. It takes odd half integral values like half h cross, 3 by 2 h cross, 5 by 2 h cross. And this particle possesses antisymmetric wave function. As I already told, if you change the any two fermions, if the sign changes, then such a wave function we are calling that as antisymmetric wave function. So all these particles have antisymmetric wave function. These particles obey Pauli's exclusion principle. Example for these fermions are electrons, positrons, protons, neutrons, mu mesons, etc. All is found to be having possessing a spin half. All these particles are otherwise called as spin half particles, and together we will call these as fermions.